Hello students, today we are going to discuss the control transfer instructions. Control transfer instructions transfers the flow of execution of the program to a new memory location specified in the instruction directly or indirectly by computation. As like before, first we will discuss the basics and then go through the instructions one by one. So let's begin. As mentioned before, these instructions transfers the execution flow of the program. So the first point to note is that the values present in the code segment, that is your CS, and the values present in your IP, that is your instruction pointer, are to be considered here. Now why is this so? This is because the physical address of the next instruction to be fetched is obtained from the content in CS and IP. So we already know that in your 8086 the physical address is computed by the value of code segment into 10H plus the value of the offset. Now when the instructions are being fetched, the segment is your code segment and the offset is your, or the index is your instruction pointer. So this is point number 1. Now point number 2, there are unconditional and conditional control transfer instructions. In the case of unconditional instructions, the execution control is transferred to a specified location independent of any conditions. So in the unconditional statement or in the unconditional instructions, there are no conditions for the control transfer, whereas in the conditional instructions the control is transferred to a particular location if any specific flag satisfies the conditions. So it can not only just be flag, but it can also be with reference to some registers such as CX. All these examples we will see when we discuss instructions one by one. So I am writing here the conditional instructions, here conditions with respect to flags or specific registers such as CX. So now that we are done with the basics, let us start with the unconditional instructions first. The first instruction is call. It is used to call a subroutine or a function from a main program. There are two types of call. The first one is called as near call and another one is called as far call. So how do they differ from each other? The near call is used for jumping to a location or control transfer to one location which is within the same segment. Okay, so therefore it is called as intra-segment call. Whereas the far call is used to transfer the control to a location which is in different segment, and that is why it is called as inter-segment call. Let us try to understand this by an example. Suppose the value of code segment is 4000H. Now for given specific value of code segment, how many unique physical addresses is possible? So let us go to our original formula of calculating the physical address. Now physical address is content of code segment into 10H plus IP. Now we know that we are having a specific value of code segment. So what is variable here? It is the content of IP which is variable. So IP can vary from 000H to FFFFH. So here we are having 16 bits which are variable. So if there are 16 bits which are variable, so what are the range of addresses which can be generated? So you can have physical address ranging from 40,000H to 4FFFFF. So this accounts to 64K unique memory locations for one specific value of code segment. Now when your code segment remains constant and the call goes to another instruction pointer, that is called as intra-segment call. Whereas for the far call, what happens is the code segment values as well as the instruction pointer value both changes. So that is why it is called as inter-segment call. So let us understand this by means of a memory map. So here we have the memory map, and first let me highlight some few basic components of this memory map, and thereafter we will try to understand the near call. So you can see here at this location you are having the code segment value, which is 4000H, and the instruction value as 5000H, which will yield the physical address as 45000H. Now this from physical address 45000H, the microprocessor will fetch the next instruction which has to be executed. So let us go to the instruction which needs to be getting executed. So as you can see, at 45000H we are having call 8000. Now call 8000, so this is a 3-byte instruction, so it will occupy 3 memory location. Call will have its own hex opcode, so that will get stored at 45000, thereby 00 and 80 at 45002H. Now we already know that lower byte goes to the lower memory location and higher byte goes to the higher memory location. So as you see here, this is call 8000. Now since only one value is provided, that is 8000H, it means this 8000 value is instruction pointer value and not code segment value. So whenever the call is provided with one value, it means that it is the instruction pointer value, and the code segment value will remain as it is. Alright, so we are clear with this part. Now come to the bottom part. We see here at this end we are having your stack. So this is your stack. So currently the stack pointer is pointing at 5008 and stack segment is F000H. So you are getting the physical address as F5008. So the stack's pointer is pointing to this location, which has already a previous value of 45H. Now when your call gets executed, so coming back to this location, okay. So when the call is getting executed, the microprocessor will fetch this 3 bytes and starts executing it. When it finds that it is only having one value, that is 8000H, so the code segment value will remain as it is, and the new memory address from which the next instruction has to be fetched will be the next physical address for the execution. Okay, so what will be the new address? So code segment value will remain same, so this value will remain same, so this is your 4000H. Okay, and the new instruction pointer value will be 8000H. So this will give you 4000 into 10 plus 8000, this will give you 48000H. Now if you see here at this point, this is your 48000H from where the new subroutine starts. So before the microprocessor jumps to 48000H to start the subroutine, it needs to update the instruction pointer and store the location from where after it needs to go back. Once the subroutine has been executed, that value needs to get stored to the stack. So if you see here, this is the value F45003. So this value 45003 needs to be stored onto the stack. But again, if you see, the code segment value is not getting changed. Code segment value will remain as it is, 4000. So the value which needs to be sent to the stack is only the value of your instruction pointer. So what will happen is, let me first clear this up. Now this your instruction pointer, this will get updated to 8000H. Okay, and this physical address will become 48000H. Okay, so the control comes to this location, 48000H. Now at this location the microprocessor should transfer the control for the execution of subroutine, but before that it needs to save this location 45003H, so that once the subroutine execution gets over, it will come back to this location. So as we have said, this in this location 45003, the code segment is same, that is 4000, only the instruction pointer changes, which is 5003. So it is the instruction pointer which will be saved and not the code segment. So the instruction pointer will be saved onto the stack. So we know that the higher byte goes to the higher memory location, the lower byte goes to the lower memory location. So 5003, so 50H will be stored first, 03 will be stored later, and the stack pointer will be updated from 5008 to 5006. So because 5006, because the stack pointer points to the top of the stack. Now with this we complete the near call. Now let me summarize the entire part. In the near call, as you would have seen, it is a 3-byte instruction. The instruction pointer is the one which is changed, the code segment remains the same, and only onto the stack the instruction pointer is transferred and not the code segment. So this completes your near call. Now let us move to the far call. Now we are going to study the far call. So if you could see the near call versus far call, everything remains the same. What changes here is this instruction. So in the previous case we have seen the instruction was call 8000 and now it is call 5000 colon 8000. So the first value, that is your 5000, this value, this is your code segment value, and the next value, that is 8000, is your instruction pointer value. Okay, so I again repeat, the first value, that is 5000, which is on the left hand side of the colon, is your code segment value, and on the right hand side of the colon is your instruction pointer value. So what will be the physical address from which the subroutine will start? Let us try to evaluate that. So your code segment value is 5000 and the instruction pointer value is 8000. So code segment into 10 will give you 50,000 plus your instruction pointer value of 8000 will give 58,000 H. Now if you see here, this is the location from which the subroutine execution will start. Now before jumping to that subroutine, what will happen? The code segment and the instruction pointer from which the next address has to be fetched or the next data has to be fetched, that will be stored onto the stack. Okay, so the next address after the subroutine execution gets over. Okay, so what is that address? Let us try to figure this out. So here you are having 45004H, call 5000 colon 8000 is a 5-byte instruction because 8000 H will take 2 bytes, 5000 will take 2 bytes, call itself will take 1 byte. So 45005, this is the memory location. This is the memory location from which the microprocessor will resume execution after the subroutine gets over. So this 45005 needs to get stored. Now if you see in the previous case, that is your near call, the code segment and the instruction pointer value, out of which the code segment value was same, instruction pointer value was different. So that is why instruction pointer value was saved onto the stack. But in the case of far call, what happens is both the code segment and the instruction pointer value has been changed because the new instruction pointer value is 8000 and the new code segment value is 5000. So let us do the stack operations. So at the first point, what will be moving is your code segment value. Now the code segment value is 4000. So first comes 40H, then we are having 00H. After that we will be moving your instruction pointer. So instruction pointer value is 5005. So 50H and 05H. So earlier the stack pointer was pointing to 5008H, that is this location, and now this will be updated to 5004H. So this completes your far call. Now let me summarize the entire thing. Your far call involves both the value of code segment as well as the instruction pointer, thereby making the total instruction to be 5 bytes in size. In this, it is an inter-segment transfer, so the code segment value will also be a different one as compared to the origin or the original location, and the instruction pointer value will obviously be different. So onto the stack, the values of the code segment and the instruction pointer has to be transferred, so 4 bytes has to be moved to the stack. So this completes your far call, and now let us just highlight the clear-cut differences between your near call and far call. So I have tabulated the differences between the near call and far call. So the first point is that in the near call it points to the subroutine within the same segment, that is intra segment, whereas for the far call it points to the subroutine within another segment, that is inter segment. And in the near call only IP needs to be stored onto the stack, whereas for the far call both the IP and CS needs to be stored to the stack. In the near call it is only 3 bytes long, whereas for the far call it is 5 bytes long. So once we are done with the call instruction, let us move to the next instruction. Next instruction is RET, that is return. Call is used along with return instruction, and depending upon whether it is a near call or far call, the instruction loads back the values of CS and IP from the stack to the CS and IP registers respectively. So for the near call, the IP from stack moves to IP register, or I can write the IP value from stack moves to IP register, whereas for the for call, the CS and IP values from stack moves to IP CS and IP register respectively. As we have already seen the memory map for call instruction, I will not be discussing the same for RET instruction. These two instructions, that is your INTN and INTO, will be covered when we are covering the next unit, that is 8086 interrupts. Next instruction is jump or JMP. It unconditionally transfers the execution control to the specified address. There are three variants of this instruction depending upon the address range covered by the jump instruction. So the first one is short jump or relative jump, and it is represented by SJMP. This allows jump to another location whose relative address needs to be specified within 1 byte. So the relative address is 1 byte in size, okay, and thus this 8-bit address needs to be specified. Now the first bit or the MSB bit is the signed bit, so we are left with 7 bits. So it gives a range of plus 128 to minus 127 memory locations. Okay, so this is the first of the jump variant. The second is called as the absolute jump. Now this allows the jump to anywhere within 2K block of program memory. So from the current location, the jump for this absolute jump can be within 2K memory locations. So whether it is plus or minus 2K memory locations. Fine. So from this you can very well guess, for this we will be needing 11 bits, because 2 power 11 results in 2K memory locations. The last one is called as long jump. Now this long jump allows the jump within 64 KB range. So it allows jump within 64 KB range. This is similar to your intra segment call. Now as we have said that it is 64 KB range, so 64 can be plus or minus 32 KB. Okay, so from the current location it can go either plus or minus 32 KB, so this will give you a 64 KB range. So this is the long jump, and how the different types of jump differ from each other, it is based upon the relative address or the memory locations from your present memory location. Now moving to the next instruction, which is IRET, that is return from ISR. It is similar to RET instructions which we have seen just few minutes back. The only difference between this instruction and RET instruction is that it is used at the end of each ISR. So IRET instruction is used at the end of each ISR. Now why is this so? Please recollect that whenever any interrupt service routine is called, it is basically a call instruction which calls that ISR. Okay, so at the end of that interrupt service routine, it needs to go back from where it has left. So that is pointed by IRET instruction. Now how is this different from your RET instruction? So the first point is that it is used at the end of each ISR. Apart from that, for the RET instruction, only your code segment and your instruction pointer values, depending upon whether it is near call or far call, that is returned to the respective registers. But for your IRET instruction, code segment, instruction pointer and the flag register contents are moved from the stack back to its respective register locations. The next instruction is loop, which executes the part of a program as many number of times given in the CX register. For example, let us see this example. So this is a small program containing 4 instructions, and its purpose is to repeatedly add the value of AX. So here we see the content of CX register is 4 or 0004H. Now when we are having this loop label, what it basically does is it checks the value of CX. If the CX value has become 0, then it will come out of the loop, else it will keep on going. So for every execution of the loop instruction, the CX value will be decremented by 1. Okay, so now we have completed the unconditional instructions and we will be moving on to the conditional instructions. In these types of instructions, the processor must check for the particular condition. If it is true, then only the jump takes place, else the normal flow in the execution of the statements is maintained. We will discuss the few important ones now. Starting with the JC instruction, which stands for jump if carry. This instruction checks whether the carry flag is set or not. If the carry flag is set, that is if CF equals to 1, then jump to specified location. The next instruction is opposite of your JC instruction, which is JNC, jump if not carry. So here the jump will go to the specified location if your carry flag is set to 0. The third instruction is JE or jump if 0. So jump if equal or jump if 0. Now when two things are equal, that is when both the things are subtracted with each other, the 0 flag will be set to 1. So here we are making use of your 0 flag. So if your 0 flag is set to 1, then jump to specified location. The fourth instruction is the opposite of your JE or JZ, that is JNE or JNZ. So jump if not equal or jump if not 0. So here the jump will go to the specified location if your ZF flag is equal to 0. The next important instruction is JP or JPE, which stands for jump if parity or jump if even parity. Let us try to understand this instruction. We know that 8086 microprocessor follows an odd parity system. So if the destination register contains even number of ones, so for example AX equals to 00100 0011 001101. So if you see, if we count the number of ones, 3 ones, 4, 5, 6, 7. So there are total of 7 ones. So this is number of ones are odd, so the parity flag in this case will be set to 0. If the AX would have contained the same thing, let me just copy this and paste it here, but instead of this one it would have got 0. So the number of ones in this case is 6, and since the 8086 microprocessor follows an odd parity system, to make the cumulative number of bits odd, this parity flag will be set to 1. Okay, so JP or JPE instruction, it means that jump if parity. So if the parity flag equals to 1, or if the number of ones are even, so that is in this case. So again you see here the parity flag is set to 1. So jump if parity, that is parity flag equals to 1, or jump if even parity, so that is even parity is this case, then the jump will go to specified location. The remaining conditional jump instruction is shown in this image, and it is self-explanatory. Now once we have understood the 5 instructions which I have just now told, if you go through the descriptions of each of these jump instructions, you can very well understand for which conditional flag it is used. Now one of the important instruction is JCXZ, so jump if CX 0. So if your CX register here is 0, then the jump will go to the specified location. So this is the only one which is quite odd as compared to the remaining instruction, which corresponds to your carry flag, whereas JCXZ corresponds to your CX register. Now moving to the conditional loop instructions. There are two variants in the conditional loop instructions. The first one is LOOPZ or LOOPE, so which stands for loop if 0 or loop if equal. So as you would have guessed, here the flag which is into the consideration is your 0 flag. So if your 0 flag equals to 1, then the loop instruction will sequence through a set of instructions. Okay, the opposite of this will be loop NZ or loop NE, which is loop if not 0 or loop if not equal. So here again, if your 0 flag is set to 0, then the loop will sequence through a set of instructions. If you would have noticed, they are similar to REP instructions which we have seen in the previous video while discussing string manipulation instructions. With this, we come to the completion of the control transfer instruction. If you have any doubts, then feel free to provide it in the comments. Also, most of these instructions will get clear when we are doing some programming questions, which we'll do once we have completed all the instruction set.